Okay, hi everyone. Today we're going to be talking about this really important foundational topic, which is called functions. Strictly speaking, this isn't a probability topic. It's more basic than that. It's something that's covered in 11th standard usually, but it's kind of foundational for the kind of maths that we're going to be doing now. And more importantly, it's a cool concept. Let's just take a look. Function is simply, you can think about it as some kind of a machine. It's some kind of thing that transforms an input into an output. You can imagine that an input goes inside a function, it transforms it in some way, and then you get an output at the end of it, right? So this is a very simple diagram for what a function does. It takes in something. It can be a number, it can be an apple, it can be a dog, it can be any number of things, and it transforms it in some way, and it can give an output. Sometimes functions don't do anything to their input. Well, they're still functions. You can think of a function as having many possible inputs. So what we have here on the left side is a set of possible inputs for this function f here that we have at the center. And as we just discussed, what the function is going to do is when it gets an input, it's just going to transform it in some way and form an output. So this is a kind of notation that is often seen, and the idea here is that the output is simply a transformed version of the input under the function f. So this is fairly standard, and mathematicians for some reason have gone very creative and used the letter f to describe a generic function. So creative, right? Anyway, here what you see is a mapping from inputs to possible outputs, which is what you could say is like the primary function, the primary job of a function. Okay, so what you have here on the left in this eggy ellipse kind of thing is you can say the set of possible inputs to this function, right? That actually has a technical name in maths that's called a domain. So the domain is essentially where you source your inputs from. It's a set from which all your inputs come from, essentially. And the counterpart in the output is called the codomain. The codomain is basically the set to which your outputs always belong. So in some sense, you can think of the domain as the source and the codomain as the destination. So a function is a mapping between these two sets. It's a mapping between the domain and the codomain, such that elements of the domain, which is what we've been calling inputs, are mapped to elements in the codomain, and therefore a correspondence is created between elements in the domain to elements in the codomain. Let's take a closer look at the ingredients that make up a function. So the first one is the domain, which is the set that is the source of the input. Then we have the codomain, which is the destination set. And finally, and most importantly probably, is a map of which inputs in the domain lead to which outputs in the codomain. This is what actually defines the transformation that a function is doing to its inputs, right? So what we have here is a classic example of a function. So this is a mathematical function, and the idea is that this x that's put within brackets of the f is the input, and what function f does is that it squares the input. So you can think of maybe the number 2 being inputted to this function f, and you get out the square of the number, which is 4. But we know that's not enough. It's not enough to specify what the function does. We also need to specify the domain and the codomain, and that's what you see here in this second line, which says function f maps from the domain of natural numbers to the codomain, which is also the set of natural numbers. What this essentially means is that this function f can only take natural numbers as input. So it can take the numbers 1, 2, 3, 4, 5, 6, and so on. But what it can't take is that it can't take the number 0, for example. It can't take -2. It can't take pi. Mind you, there's nothing stopping us from actually squaring 0 or squaring -2 or squaring pi or 3.5 or any of these numbers that actually don't fall within the domain. Uh, uh, there's nothing actually preventing us from squaring them, but the fact is that the way we've defined this function, we're putting that constraint that this function can only take in natural numbers. So that's important to note. So one way you can write this function, one way to represent this function is to use a table as such. You can have the input values on one column and the output values, corresponding outputs, on the other column. And the more I would say the more reasonable or the more important way to represent these is by using the Cartesian coordinate system and graphically representing what a function does, which is something we see very often in mathematics. So we best get used to it. And the idea is we usually plot the input on the x-axis and the output on the y-axis. And so for our function here, this would look something like this, and so on. I don't have enough space for the other points, but they would basically go somewhere here. It just keeps going higher and higher. There's one caveat to functions. There's one very important requirement of a function that we haven't spoken about yet, and that requirement is this: any given input to a function can have at most one output. So if a mapping fails to satisfy this constraint, then it cannot be called a function. Well, we'll take a look at an example of that. So let's say you have a machine G, much like the machines we've been talking about so far, which is basically something that takes an input and spits out an output. And let's say this is what G does to its input. Okay, so it takes its input and it raises it to the power 1/2, and that is essentially its output. So mathematically, if you look at this, raising a number to 1/2 is equivalent to taking its square root. That's what it means basically. And we do know that square roots come in two flavors. There's a positive square root and a negative square root, and that's kind of going to make this problem kind of interesting. But first we also need to specify where G maps from and to, and here it maps from the real numbers to the set of real numbers. So say you have the input 4. Okay, now think about this for a minute. What would G do when we give it input 4? And the thing is, G does not have a single answer to give us. It gives us both +2 and -2, and that is a problem for us, because if you look closely at the requirement here, for a mapping to be a function, it can have at most one output for a given input. So we gave it the input 4 and it did not give us a single output. Therefore, G cannot be a function. Let's take a look at another example. Say you have this mysterious looking machine called Whitener, and this is what it does. You throw a blue ball inside, you get a white ball. You throw a green ball inside, you get a white ball. You throw an orange or saffron, I don't know what that is, doesn't matter, you get a white ball. Is this Whitener thingy a function? Pause the video a minute, maybe, to think about this. And based on what we've seen of functions so far, we know that they need to be a few things. We do know that they need to be a mapping between an input space and an output space, which isn't like odd here. It is definitely mapping some inputs to some outputs. So let's see what that is. So we can think of the 3 colored balls as our domain and the white ball as the codomain, which is the entire set of possible outputs. We also need a relationship between the two, such that you know which output you would get given an input, and something like that can be described by this arrow diagram that we have here. And what this is simply showing us is that no matter which of these colored balls you throw in, you always get the white ball. Please think about this question. Is whitener a function? And to answer this, you need to answer the more specific question, which is, does each individual input map to at most one output? So you need to think about each individual. You need to individually think about the blue ball, the orange ball, the green ball, and think whether each of them, do they map to at most one output? Is there any of them that maps to more than one output? And it turns out no, each of them have a single output. Individually speaking, there is no more than one arrow poking out of each of the colored balls. That means that this is a valid function. Let's consider this. Take a look at this and think for a minute and try and answering the question, is this a function? We ask ourselves the same thing. Does each individual input map to at most one output? And you see the blue ball here has two arrows poking out of it to two different balls. That violates our principle. Therefore, this mapping, whatever it is not a function. Now I want you to take a look at these three other relationships, mappings, and pause the video and think about it. Think about each of these and answer to yourselves whether they satisfy the criteria we established so far of what it is to be a function. Okay, so these are the answers, and this one might surprise you a bit because two of these balls have no outputs. They're being mapped to nothing. It's as if you throw them in the machine and nothing happens. That's actually okay. It's not necessary that every point in your domain has to map to something, but it is important that none of the points in the domain map to more than one thing. So what did we learn about functions? A function is a mapping between two sets. Elements of the domain are mapped to elements in the codomain. An element in the domain can have at most one element in the codomain to which it maps.